This presentation will cover half-life activity and positron emission tomography as part of the radioactivity section of this chapter. The following are the learning outcomes required by SACE, and they'll be covered in the following presentation. Even a very small piece of material contains a large number of atoms. So 0.001 of grams of carbon-14 contains 10 to the 20 atoms. Now when we're talking about the decay of atoms, we don't know when an atom will decay. All we know is that all the atoms in a material won't decay all at once, and the number that do decay depends on the number present. Radioactivity is a random process with a constant probability of decay. What this means is that for a given material, we can determine the rate at which all the atoms in the material decay. Now let's define half-life as the time taken for half the atoms in a material to decay. Looking at our graph, if we originally start with N0 as the number of atoms, after one half-life, we are left with half that number. After two half-lives, we are left with half that number. So half of N0 on 2 is N0 on 4, so we're down to a quarter. And you can see this is an exponential decay as given by this function. Let's look at an example, starting with the bottom picture first. So we start with 100 kilograms of some sort of material that has a half-life of 86 years. Now, and this is represented by 24 dots. What this means is after 86 years, we can predict that we're going to be left with half that. So we're left with 50 kilos, or 12 dots in this example. Now, another 86 years after that, we get half that number again, and we can keep going for the life of the material. As half-life activity is a nuclear process, the environment has little effect on the rate of decay. So it doesn't matter if we've got an oxygen atom that is bound covalently in a water molecule, if that water molecule is located either under the polar ice caps or in a bottle of wine, it will decay independently of the environment. So using this information, this allows us to compare the age of fossils as one application. To determine the age of a material, two methods of investigation can be used. So the first is to determine the number of atoms in the sample. Now this can be very difficult when the atom has, or the material has a half-life that is really short, because during the measuring process the number of atoms will change. Now this method is mainly used for materials with half-life over 10,000 years. Now the other method is to measure the activity of decay. Geiger counters are a tool that can measure the radioactive emissions of a material. So not in the syllabus, but the way they work is that we have a radioactive material and a probe with a gas inside. Now when the emissions from the radioactive material occur, they can collide with the atoms inside the probe and promote electrons. Now these electrons will go from the anode to the cathode and create a current. And now this current is measured and counted and can determine the number of radioactive emissions. Now the activity of decay is the number of nuclear decays per second and has units of becquerels. So 1 becquerel is 1 decay per second. So an example, if a Geiger counter measures 180 alpha particles in 2 minutes, then the activity is the number of alpha particles divided by the number of time. So it's 180 over 120. Remember that our conversion to seconds is always used in physics, so it'll be 1.5 becquerels. Now this method is more useful and is less complicated than the counting atoms method. It's more portable and requires less instruments. So now we'll talk about positron emission tomography, which is the application component of this chapter. So traditional methods of investigating the body are destructive, meaning you have to cut someone open to have a look inside, or they only show structural detail, such as X-rays. So what PET does is gives a detailed picture of the body. To do this, radioisotopes are used. So a bit of background about how the body works. The body doesn't distinguish between isotopes when it's performing its functions. So for example, if glucose requires oxygen, the body will take either the radioactive oxygen or a stable oxygen, whatever it can get its hands on. Fluorine-18 is a commonly used isotope in medicine, and it is created by firing a proton at an oxygen atom, as shown in the top nuclear reaction. Now this fluorine-18 has a half-life of 110 minutes, and when it decays, it produces positron. This positron collides in the body with an electron in the tissue. Now this process is a reaction called the positron-electron annihilation, and what happens there is that the mass is actually transferred to energy and two gamma rays are produced. Now these gamma rays, according to the conservation of momentum, travel in opposite directions. So looking at the positron-electron annihilation, we have the mass of the two particles, which is given here, and this mass is obviously converted to energy, being those two photons. So using E equals mc squared, we can find the energy in this reaction is found here, is given there. But this is shared between the two photons, so half of that is the energy of one photon. Active areas of the body, such as areas of cancer, will absorb a lot of radioisotopes. Now, in these areas, there will be a lot of positron-electron annihilations, and the PET scanner can determine the location of these. So what happens is the body is located in the center of a ring, and the ring actually can determine and detect the gamma rays that occur from these annihilations, and using calculations can determine the location of where that positron-electron annihilation occurred. And with this information, doctors can use this information to determine the active areas in the body. As part of the syllabus, you're required to know some applications of some specific radioisotopes. So oxygen-15 is constituted into water and is used to monitor blood flow through tissue. Fluorine-18, which is what we looked at before, is attached to glucose molecules and used to monitor brain and heart functions. Now these PET machines are not used very often because the half-life of the material that is used for these radioisotopes is very short and has to be used in the location where it is made. So in Australia, there's a reactor that can make radioisotopes in Lucas Heights, and just recently in Adelaide we got one at the bottom of the cheese grater building, the SEMRI Institute, that can produce radioisotopes for research too.